This video is sponsored by Squarespace.
The standard model of particle physics is the best theory we have for how the universe works on subatomic scales. It's not even a close competition, like LeBron versus a snail in a dunking contest. No other theory is as good at describing the particles that make up reality and how they interact with one another. But despite how impressive the standard model is, it is also wrong. And it's wrong in ways that leave some absolute whopper mysteries for scientists to solve. So here are 5 of the biggest problems with the standard model, as well as some ways that physicists are trying to patch the cracks. In 2013, 2 physicists won the Nobel Prize in Physics for predicting the existence of a single subatomic particle, the Higgs boson. They made their predictions back in the 1960s, but the Higgs boson wasn't officially discovered through experimental observations until 2012. The Higgs boson helps give all the other subatomic particles their mass, so the standard model just doesn't make sense without it. Hence why physicists spent so long trying to find it. In the annals of particle physics history, this was just one of the many times the standard model described a thing before we actually knew it existed. And by we, I mean humanity as a collective, because, some of us were too busy not being born or being teenagers to contribute. But for the Higgs boson, there was one major problem. The particle that CERN discovered had a mass of 125 giga-electron-volts, or roughly 130 times the mass of a proton. That might sound kind of big for a single subatomic particle, but it's too light. Much too light. It might be as many as 34 orders of magnitude too light. That's 10 million billion times what it should be. Now I had to pull out the scare quotes because the standard model can't really predict the mass of the Higgs boson at all, because the equation for its mass depends on a number that's unknown. It's called the UV cutoff, and it's the point at which the energy levels of the thing we're observing are too high for our math to work. But like I said, we don't actually know the exact value of the UV cutoff. It's just vaguely over there somewhere. Since we don't actually know that number, our theories have to work for all possible values of the cutoff, including really enormous ones, which means the equation would need equally enormous negative values somewhere else to balance that out and give us the mass we've observed for the Higgs boson. What could cause this uber-convenient cancellation? We have no clue. And unfortunately, that means we've run into a case of fine-tuning, and fine-tuning gives physicists the willies. It's not impossible that nature could so carefully and so precisely balance the energy checkbook of the universe, but when a theory requires such a precarious balancing act, physicists get jumpy and try searching for something entirely different. One of the leading ideas to explain the mysteriously normal-sized Higgs boson is supersymmetry. We don't have time to get into the physics of exactly how it helps, but it poses there's a whole set of particles lurking at energies higher than we've been able to create in experiments. These new particles would be paired with standard model counterparts, like traditional quarks would be partnered with supersymmetric squarks, and leptons would be partnered with, yes, sleptons. These new guys have some properties that are opposite from their standard model partners, and this oppositeness shows up in our equations as a minus sign. So if supersymmetry particles really do exist, the calculation for the Higgs mass would better agree with what we actually observe, without scientists just having to add a number without knowing why it should be there. There's still no solid evidence of supersymmetry, so physicists are tracking down other potential solutions too. At CERN, they're even searching for more Higgs particles, because some new theories allow for more than one type of Higgs boson. But for now, the fine-tuning problem persists, and it persists for our next problem with the standard model, because as it turns out, the universe is expanding way too slowly compared to what the standard model predicts. And by way, I mean as much as a 1 followed by 120 zeros times too slowly. This is sometimes called the worst prediction in the history of physics, because this is just an unbelievable degree of wrongness compared to our observations. But let's back up in case you missed the news flash from the late 90s. The universe is not just expanding, which we've known for almost a century now, that expansion is accelerating. This discovery also earned a Nobel Prize in 2011, and this is the last time I'll mention the Nobels, promise. In other words, the universe is perpetually getting bigger, faster, so something must be fueling that expansion. Scientists call this mysterious something dark energy, and they have no idea where to go from there. One of the simpler hypotheses relies on the standard model's assumption that the universe is filled with vacuum energy, basically the energy that just comes with everything in the universe just existing. The problem is the total amount of vacuum energy in the observable universe should be causing the universe to expand so fast that nothing of substance could exist. Even individual atoms would struggle to form in such an environment, let alone things made of many atoms, like stars and planets, and those tiny little porcelain trinkets that your grandparents maybe collected. And to be honest, I think they were kind of onto something. Like, there's something so fun about having just like a little tiny delicate trinket in your hand and putting them on a shelf and, stacking them up, and then you can just sit back and look at all of them and at best, theoretical physicists can reduce that 10 to the 120 discrepancy between what the Standard Model predicts and what astronomers actually observe down to 10 to the 60. It involves some of that supersymmetry I talked about earlier, but it's nowhere near helpful enough. For now, we've run into another fine-tuning problem. It seems like there should be some other number in the appropriate equations with a power of negative 120 that cancels out almost all of the predicted vacuum energy. And again, scientists would rather find a more natural solution, but when it comes to potential solutions, they're still throwing spaghetti at the wall. And so far, not much has stuck. One set of ideas involves quantizing space. Most of our theories are built on the assumption that the universe is a smooth, continuous fabric, even down to the smallest scales of reality. But maybe that's wrong. Instead, space-time might be made of discrete quantized chunks, like pixels. This would alter the calculations we'd have to do for the strength of vacuum energy, and we might wind up with an estimate much closer to observations. Another possible solution relies on reimagining the structure of the universe as a sort of frothing quantum foam. On the very smallest scales, space-time could actually be full of holes that pop in and out of existence, like the foam on a pint of beer. These fluctuations could disrupt the Standard Model's vacuum energy calculations and cause the vacuum energy to be far less than current predictions. While both of these solutions are technically allowed within the boundaries of modern physics, they both have one major disadvantage. They're really hard to test, because they involve measuring distances that are 20 orders of magnitude smaller than a proton. Some scientists doubt we'd ever be able to test them. But that's no reason to quit while we're behind, because this isn't the only time the Standard Model has thrown us something that's nearly impossible to study. When it comes to neutrinos, the Standard Model has very little to say. It tells us there are 3 kinds, or flavors, of neutrino, and their 3 antimatter counterparts. It tells us they're all electrically neutral, hence their name, and it tells us they're impossibly tiny, even where subatomic particles are concerned. But it can't tell us how tiny, either in terms of the space they occupy or in terms of their mass. In fact, the Standard Model originally predicted neutrinos don't have mass at all, except we know from experiments that they very much do. If they didn't have mass, neutrinos wouldn't be allowed to occasionally swap what flavor they are, which physicists figured out over 2 decades ago and got a Nobel Prize for it in 2015. Okay, sorry, that was the last time I'm gonna reference the Nobel Prize. There are so many mysteries surrounding neutrinos, and SciShow keeps covering them. We're still not done, because in this episode, let's focus on a decades-old question mark called the gallium anomaly. Buried beneath the mountains on the border between Georgia and Russia is the Soviet-American gallium experiment, or SAGE for short. The actual experiments involved bombarding a sample of the metal gallium with a bunch of neutrinos. Every once in a while, a neutrino would collide with a neutron inside the gallium atom, and turn the neutron into a proton. Since it's the number of protons that determines what element you are, this collision also turned that gallium atom into germanium. However, when the researchers actually counted up their germanium, they found about 20% less than they predicted. Those predictions, of course, were based off the Standard Model's version of subatomic particle interactions. Despite their best efforts, SAGE researchers have been scratching their heads over this discrepancy since the 1990s. In 2014, they even built a follow-up experiment called the Boson experiment on sterile neutrinos, or BEST. One of its goals was to check whether the gallium anomaly could be chalked up to experimental error, like miscounted atoms or miscalculations in the expected rate of neutrino-neutron collisions. The good news? The experimental results held up. They even improved on SAGE's in terms of quality. But that also means bad news. The researchers were left with all of the exact same questions about why this anomaly exists at all. So far, the only maybe sort of feasible solution that physicists have proposed is a new 4th flavor of neutrino that the Standard Model doesn't account for: sterile neutrinos. All neutrinos are notoriously evasive. A neutrino could pass through a light year of lead with only a 50% chance of bumping into anything along the way. But sterile neutrinos would be even more ghostly. The only way they could interact with anything was through gravity, because like the 3 traditional flavors, it would need to have mass. That way, they could also participate in all that flavor swapping. Maybe that germanium is missing because 20% of the neutrinos happened to turn into sterile neutrinos at the wrong time and refused to interact with the gallium at all, instead of just incredibly rarely. Unfortunately, before you get too excited about the possibility of sterile neutrinos, there is a catch. The kind of sterile neutrino you'd need to solve the gallium anomaly is a much lighter version than what most scientists are currently looking for. Other experiments have searched for light sterile neutrinos in this mass range and have come up empty. So if sterile neutrinos do exist, which physicists have proposed to answer other problems with the Standard Model, they might all be super heavy. In fact, there's a new neutrino experiment called Juno that came online in China in August 2025. They're planning to precisely measure neutrino flavor swapping, and maybe the info they gather can help us fix the next problem with the Standard Model. But before we get to that, we have the standard problem of paying the bills. So here's a quick ad.
Thanks to Squarespace for supporting this SciShow video. Squarespace has introduced AI tech into their products, which SciShow viewers are bound to be curious about. The idea behind design intelligence is to unlock your creative potential. Now anyone can build a beautiful, more personalized website tailored to their unique needs. Squarespace also offers flexible website templates, so you can have a website that looks professionally designed, because it will be. And you can't put amateur effects on that kind of professionally designed website, so Squarespace also gives you an elevated suite of visual design effects that will fit right into your new site. Head to squarespace.com for a free trial, and when you're ready to launch, go to www.squarespace.com/scishow to save 10% off your first purchase of a website or domain.
Do you exist? Congratulations, you're evidence that the Standard Model is wrong. Because at the dawn of our universe, both matter and antimatter should have been popping into existence at the same rates. But if matter and antimatter twins annihilate when they get too close to each other, then all the universe should have been filled with for the rest of time is a bunch of light. Well, technically there'd still be a bit of quantum particle shenanigans, but I mean no galaxies, no stars, and no tiny little porcelain trinkets like the ones your grandparents might have collected. And I'm honestly hoping that I inherit my grandparents' collection, because I think that'd be really special and sentimental, in addition to the ones that I thrift. And it looks like matter won the battle. Although not by much. For every 1 billion antimatter particles, just 1,000,000,001 matter particles must have been created. But before we can theorize about how this came to be, we need to back up a little. There's a symmetry in nature that is, for the most part, respected. It's called charge parity, or CP symmetry. Physics should work the same if you flip all of the particles with their opposite charged antiparticles, and also flip the definitions of left and right. After all, positive versus negative and left versus right are just human terms that we made up. Those definitions should not affect the physics going on. But I do keep saying should, because researchers have discovered a couple situations that violate CP symmetry. Antimatter fundamentally behaves differently than matter does. They aren't exact counterparts. And despite what you might think, the Standard Model is kind of okay with that. In fact, it predicts CP violation could happen in certain weak force interactions. In other words, situations where unstable subatomic particles are decaying into other stuff. However, the amount of CP violation predicted by the Standard Model can't account for all of the asymmetry that allows us to exist. So far, the only place we've observed CP violation is in the behaviors of particles made from quarks, a class of subatomic particles that includes the stuff inside protons and neutrons. While the Standard Model is good at explaining this particular case of CP violation, we need something more to fully explain the matter-antimatter asymmetry. So guess who's back to maybe save the day? Neutrinos! Physicists suspect that the violation they observe in quarks also happens with a different class of particles called leptons. The most famous lepton is the electron, but neutrinos are leptons too. We don't have time to get into the details here, but if scientists found CP violation in neutrinos, it could unlock the theory for a process called leptogenesis, which provides a mechanism for generating more matter than antimatter during those early years in the universe. Or maybe we don't need neutrinos at all. The answer to our asymmetry problem might be hidden with the quarks, because according to a paper published in 2025, experiments conducted at CERN found far more CP violation on the quark side than had previously been observed. Or maybe there's something else completely beyond the Standard Model to uncover. But in terms of elements missing from the Standard Model, we have to end on what's arguably the most glaring. Gravity isn't in the Standard Model at all. perhaps the most obvious of the physics' 4 fundamental forces in our day-to-day lives. Not that the electromagnetic, weak, and strong nuclear forces aren't critical to our existence, of course, but come on, babies learning to lift their heads up know about gravity. It's so different because, at the moment, our best understanding of gravity comes from the theory of general relativity, in which gravity isn't technically even a force. Instead, GR tells us that it's a side effect of mass creating curves in the fabric of space-time. So gravitational force, as we currently understand it, is more geometric in nature. GR's version of gravity also lacks a messenger particle, a particle that ferries the force through space and time. The electromagnetic force has the photon, the weak nuclear force has the W and Z bosons, and the strong nuclear force has gluons. Each is described thoroughly by the Standard Model. Some researchers have proposed the existence of gravitons for gravity, but there's no evidence that they really exist. Even if they did, there's still another pretty glaring mystery about gravity relative to the other forces. It is so much weaker. A cheap fridge magnet defies the gravitational pull of the entire Earth. Easy peasy. And the gravitational pull between 2 electrons is about 43 orders of magnitude weaker than the electromagnetic force pushing them apart. Sure, that's no 10 to the 120, but it's still an enormous gap. One way to bridge this metaphorical canyon is by adding extra dimensions to our theories for space-time. The universe we experience is made of 3 spatial dimensions and a 4th dimension for time, but maybe space-time has additional dimensions curled up and hidden because we're just too darn big to perceive them. Imagine walking a tightrope across our metaphorical canyon. You can only move forward or backward, but if an ant decided to follow along for moral support, they'd be small enough to also move left and right, perhaps to better evade your feet as you inevitably lose your balance. If space-time really does have extra hidden dimensions, they'd only be observable using very, very large amounts of energy. So much energy, perhaps, that no experiment on Earth could ever reveal them. But if these dimensions exist, then gravity might be much stronger than we think. It would just have to spread itself across the many different spatial dimensions. That would dilute its full strength so that we, in our 3D subsection of space, would only observe a minuscule fraction of it. Or remember those theories that quantize space and might help us understand the universe's expansion? Well, they could also help explain how gravity fits in with the Standard Model. But we're technologically just as far from understanding quantum gravity as we are from finding any hidden dimensions. There is one argument that could explain not just why gravity is so weak, but many of the problems we've talked about in this episode. The anthropic principle says that the universe is the way it is because we're here to witness it. If conditions were just a little bit different, if gravity were just a bit stronger, if the universe were expanding just a bit faster, if all the matter and antimatter completely annihilated at the beginning of the universe, then we couldn't ask why, because none of us would exist. So it has to be this way. That sounds like a lot of fine-tuning to me, with a bit of circular reasoning thrown in there for good measure. It also sounds like a boring way to answer some really interesting questions. There's plenty to learn just by searching for answers, and getting unexpected results is part of the excitement of science. Maybe someday we'll have updates on these 5 problems with the Standard Model, and when the news does break, you can be sure there'll be a SciShow video about it.